Greetings, physics fans. We left off last time presenting the magnificent Maxwell equations. And no, this is not a set of equations that you'll ever be using in this course. These are way too advanced for that. But the purpose of showing these was to show how we get to our next level of understanding, this next realm of problem solving we're going to do. Right? And we summarize all the different laws we've studied that got us here. And now for the new material, right? You see how we have these things like the rho here, or this J here. These are what we call current and charge densities, right? Specifically, rho is the charge density, and J is the current density. It just means the charge per volume, or current per volume, right? And we're going to do something interesting. We're going to set them to 0, i.e., we're going to go to the vacuum space, is another way to phrase this, okay? And what happens there? Well, this equation, this one, changes to just del cross B. This means the curling, a rotating magnetic field, is generated by a mu naught epsilon naught del E del T. This should remind you of our laws of inductions, that if one guy's changing in time, it's inducing another one that's rotating. Think of the current through a long straight wire. It's a rotating magnetic field. And we're left, what is this quantity? Mu naught epsilon naught. All right. So as a reminder, epsilon naught, our electric constant, that is a 8.85 times 10 to the minus 12th farad. Name for it is the electric permittivity. The electric permittivity constant. Mu naught, a little bit easier to remember number-wise. Come on. It is 4 pi times 10 to the minus 7th henries per meter. This is called the magnetic permeability constant. All right. So let's calculate this product. Let's see what this is. You know me, I'm a units guy. I want to know, does this have any physical significance, or is it just a bunch of crazy units stitched together? So this is going to be a farad meter times a Henry meter. Farad, unit of capacitance. If you want an equation, remember that. Capacitance was defined as the charge per voltage. A Henry is the unit of inductance, our last section. If you want an equation, remember that. An EMF, this comes from a modified Faraday's law, is L, change in current, change in time. So we can rewrite these. I can say, instead of a farad, I'll call this a coulomb per volt per meter. Henry is going to be replaced with a volt second ampere per meter. And I'll visually highlight this just to help with the substitution. So we went from farad to this, and then Henry to that. That's what we're doing. All right. So let's simplify this, right? I automatically see voltage, so we're going to cross those out. And we'll reduce this down to a coulomb times the second per meter squared amp. And recall that an amp is just coulombs per second. So coulomb second meters squared. Let's make that one a little bit legible. Come. Meters squared, this is a coulomb per second. So we've canceled out the units of coulombs. We have this strange thing, second squared per meter squared. So not mu naught. So if I phrase this in a slightly different way, if I say, hey, let's look at the square root of epsilon naught mu naught, 1 over that. Well, that is units of meters per second, which is the velocity. Excellent. We've got velocity out of this epsilon naught mu naught quantity that it popped out of Maxwell's equations. Well, these are constants. Let's calculate what this is equal. 1 over square root epsilon naught mu naught. Let's plug in the values. 8.854, 10 to the minus 12th Farads per meters. Never forget your units. Times a 4 pi 10 to the minus 7th Henry per meter. We're going to square root that quantity, evaluate 1 over that, and we'll find this is 2.998 times 10 to the 8th meters per second. For those of you who don't remember, this is the speed of light. Amazing result, guys, amazing. Epsilon naught mu naught is equal to the speed of light. It just pops right out of the field equations. And we'll label out the quantity C here. Speed of light, C. Absolutely spectacular result. So let's talk about this a little bit. All right, we just said look at our electric magnetic equations. Faraday's law of induction, first thing that tied them. Ampere's law, which we didn't properly define when we were in the magnetic chapter, but it was still there. It was showing that a moving current produces magnetic fields. They're connected. Electric and magnetic fields are connected, and they're connected by light. Light is the connecting thing between them. So, before we can do the discussion, let's talk about this number, this speed of light. Specifically, how fast is the speed of light? Come on. Wake up. All right. All right. I think it's absolutely critical that everyone has a comprehension how big these numbers are. 2.998 times 10 to the 8th meters per second is big number. Like, it's just fast. Let's put some context to it. So, for the purpose of this class, we're going to approximate, we're just going to call C 3 times 10 to the 8th meters per second. We're not doing high precision experiments. 3 times 10 to the 8th is good enough for us. All right. Now let's compare this with the circumference of the planets. So let's get ourselves a nice little globe Earth. And there's the radius of Earth. And I'll just tell you now, the radius of Earth in meters is 371 times 10 to the 6 meters. And now let's look at the circumference. If I was to calculate the circumference of Earth, right? I'll leave out the capital C. And that circumference is equal to 2 pi r, which to 2 sig figs, yes, here I'm right, it's 3. 3 sig figs is 4.00 10 to the 7th meters. So let's compare this distance with the speed of light. So C is in the speed of light is 3 10 to the 8th meters per second. And now I'm just going to change units. I'm going to say multiply by 1 Earth circumference and then divide that by what that's equal in meters. 4.00 times 10 to the 7th meters. Right? 3 divided by 4, carry the factors of 10, and we'll find that this is 7.5 Earth circumferences every second. Per second. All I've done is change the units on C. Instead of expressing it in meters per second, I expressed it in Earth circumferences per second. So what this means is that in less than a second, in less than 1 second, light will travel the circumference of Earth 7 times in less than a second. A second, we've gone halfway around again. So in less than 1 second, light travels the circumference of Earth 7 times. That is how blistering fast the speed of light is. Start putting the universe to scale. The moon, it is 1.3 light seconds away. It takes light more than a second to get there. The sun is about 8 light minutes away. So, there we have summarized just how insanely fast the speed of light is. So let's keep going. Let's start building new material. There we go. So, emphasis. Light. It's what we call right? That means it's a combination of oscillating electric and magnetic fields. Right. An important caveat. This one's you're going to want to remember. In vacuum, right? Not traveling through air, just in vacuum, nothing else around. That electric magnetic field are just related by the speed of light. Speed of light. That's the relationship between electric and magnetic fields. E equals C times V. Graphical way to represent this, right? We'll call this S. You'll understand why later on. Here's B, and here's E. And what's happening? The electric field changes. It oscillates sinusoidally. It'll increase, then decrease, increase, decrease, increase, so on and so forth. Let's try that. Come on. There we go. Just recent, I want a cleaner curve. So I'll do this a little bit faster. There we go. Well, whenever the electric field is changing, electric field is constantly changing. It's going up, down, up, down. The electric field is changing by Faraday's laws, Maxwell's laws. No, Faraday's, Ampere's, Maxwell's laws as the catch-all. By those laws, if there's a changing electric field, there must be a changing magnetic field. And it turns out to be perpendicular, always perpendicular. So you're going to get this magnetic field that's oscillating like this, back and forth, forever and ever. You think of little vectors to represent the length as you're propagating at any slice of time. This is what magnetic fields are doing. And your electric fields are similar, but rotated 90 degrees. So there is our simplest electromagnetic wave propagating down. With this propagation, and that wave has to be traveling at the speed of light. At speed c, going that direction. So, by combining electromagnetic fields, we've created waves. Those waves turns out to be light itself. So let's start talking about some wave properties. All right. Let's draw the simplest sinusoidal wave I can think of. And we can measure things like the wavelength. I call this x. Right. Wave amplitude. I can say there's this wavelength with a lambda, lowercase lambda. That's the wavelength. The wavelength itself is measured in meters. It's a distance measurement. We also say we have the frequency, how quickly, how frequently it bounces up and down. Right. Frequency, the number of oscillations per second. Units of frequency is be called hertz. 1 hertz is just an inverse second. If you want to be specific, it's actually a oscillation, 1 oscillation per second. But in shorthand, we just say inverse seconds is what a hertz is. All right. Now our waves can propagate. They can move. So I could have a wave that was here. So the dashed line represents where it used to be. And then say, well, wait some time and now it's over here, like this. All right. So the wave itself is moving with some velocity. The wave propagates down. Well, the wave speed is simply just the product of the wavelength and frequency equals lambda f. And this is true for any wave. But since we're dealing with light waves, we get a nice, useful modification to this. We'll actually write it as c times lambda f, the speed of light times lambda f. And notice that definition, laws of physics. The speed of light is constant. This is going to come up very important for us shortly. Let's see this in action, right? Let's say I'm going to compare ultraviolet and infrared rays, right? So, ultraviolet. What I mean is rays above the purple spectrum. Purple being the visible spectrum our eyes can see, and I'll elaborate a bit more on this in a moment. But ultraviolet rays have a wavelength of lambda UV, that is 100 nanometers. And I'll change this into the purple color to help out with that. Come on, change colors. There we go. And now let's compare that with an infrared rays. Right? Infrared rays have a wavelength of 1 micrometer. So the question is, which wave has the greater frequency? Right. Now I could use the speed equations to just explicitly calculate the values, but I don't care. Like, it's hard to use a calculator. Let's just use numbers that we can do on hand. Who needs a stinking calculator? So let's write this out. We'll say lambda UV F UV. For waves propagating in space, that must be the speed of light. But infrared rays are still a type of light. So I could say lambda IR, F IR. Well, speed of light's the same for both types of rays. So let's just cut out the middleman. Get rid of the C. And let's just compare the frequencies now. Which one's bigger? Well, FUV is equal to lambda IR over lambda UV times lambda, or FIR. So let's plug in our values. Lambda IR, that was 1 times 10 to the minus 6 meters. UV, well, that's 100, 10 to the minus 9th meters, times whatever the frequency of the infrared ray. Oh, let's count out powers of 10. This is 1 times 10 to the minus 6. There's a minus 9 in the denominator, so that becomes a plus 9. And there's 100 in the denominator, which gets us to a minus 2. So altogether, minus 6 minus 2 is minus 8, plus 9. This is 10 to the first power. 10 times FIR, FUV. The ultraviolet wave has a frequency that is 10 times greater than the infrared. So the takeaway from this, speed of light is constant. Never forget that. Right. So the result of this is that wavelength and frequency are inversely proportional. Okay? So long wavelengths, the longer your wavelength, the lower your frequency. And correspondingly, high frequencies have short wavelengths. So let me pull up a nice little chart that does a great job summarizing just the electromagnetic spectrum. Let's pull this guy in here. All right, gotta make that a little bigger. Hold on a second. So there we have it. This whole picture is a capture of what we mean by the electromagnetic spectrum. Let me highlight little bits here and there. You see this region here. That's what we call the visible spectrum. Why I call it the visible spectrum? Well, that's what our eyes see. That's what we see. Then you can have the infrared. Right? That's the colors, the wavelengths that are shorter. They have longer wavelengths than red. They're below our ability to see. We associate temperature and glow with around temperatures, wavelengths at this, lights at this wavelength. And then we have the ultraviolets. Or the above violet. So we can see up into starting in the purples, and then the wavelengths get too short. We can no longer see those. Our eyes just don't absorb those photons, or those photons don't get to us on Earth. So we don't see these anymore, but these are the higher energy photons. So emphasis. Low energy, high energy. If any of you like to suntan, do you put yourself under a heat lamp or an ultraviolet light? You use the ultraviolet lights, okay? These are the photons you're going to use if you want to get a nice little tan. Now, if you want to get ionizing radiation, if you want to harm yourself, well, go further and further in this spectrum. All right? So you can have, we'll go through the electromagnetic spectrum together once. Our longest, I'm going to talk about the wavelength. The longest wavelengths are going to be the radio waves. This is what we use to communicate. All of our devices communicate through radio waves. These can be wavelengths that are upwards to kilometers long. These are long, lazy wavelengths. They do a great job of transversing the cosmos. They penetrate walls. They penetrate buildings. Keep going up spectrum. We'll have microwaves. So we're going to shorter and shorter wavelengths. You got microwaves, right? Heat up your food. I imagine a lot of you are doing that right now. Infrared. That's what we tend to associate with glowing temperatures. Right? The hotter something is, the greater thermal photons it gives off. We tend to associate that as infrared because that's about what we glow in. We're all glowing right now. Keep going. You get to our visible spectrum. These are on the order of nanometers. And then ultraviolet, X-rays, gamma rays. So as we sweep the electromagnetic spectrum, the wavelength keeps getting shorter and shorter. So let's try problems. Let's solve the question. All right. Question. So right now I'm using a wireless mouse, and I imagine lots of you have wireless devices, right? So I have a wireless mouse, And it uses a 2.4 gigahertz signal to work with my computer or to communicate to my computer. All right. So, question. What's the wavelength? What wavelength of light is my mouse constantly radiating out right now? Well, straightforward. If C is equal to F, I know C, I know F, let's calculate lambda. That is equal to C over F. So that's going to be 2.4 times 10 to the gigahertz, 10 to the 9th hertz. All over speed of light, which we say is 3 times 10 to the 8th meters per second. And I'll find that this is a wavelength of 1.25 times 10 to the minus 1 meters. Converting that in more appropriate units, I'll say that is 125 millimeters. Devastating wavelength. Not really. All right, follow-up question. What type of wave is this? So let's scroll back up a little bit. We know the wavelength and frequency, so let's just find them on our spectrum chart. We're looking at something that is 10 to the 9th hertz. 10 to the 9th hertz. Well, I see 10 to the 8th, and that's below the microwave range. And 10 to the 12th is where we are infrared range. So this falls in just a category of what we call an infrared photon. It's infrared. Emphasis. A big point I want to make here. Infrared photons, they're not harmful to us. They pass right through us. They're not damaging. So we're not terribly concerned about having tons of these wireless devices around us because honestly, the cells that make up our body don't interact with infrared photons. We don't really absorb them. So let's box this in and continue on. We're talking about waves. We're going to need to start discussing what we call wave fronts. All right. Before I start going, I just want to point out here that there are literally shelves and shelves of textbooks dedicated to this subject matter here. So we're going to gloss over the fundamentals, the basics, but you literally could spend an entire life's work exploring just this range of material by itself. So, like I said, let's do our fundamentals. Let's start mathematically describing our waves. So the simplest wave possible, little one. You've already seen these a little bit. So here's what I'm going to do. We'll have X, Y, and then coming out of the page here, Z. We need to keep thinking in 3 coordinates, guys. Let's have our wave. We'll have the electric field propagating in the Y direction. Right? Electric field is going up and down the Y direction. And then the wave itself travels in the X direction. So what is our magnetic field doing? Well, it's doing this. I'm using cross and dots to represent which way it's pointing, and then the size for its magnitude. So that's our magnetic field, right? Come on. So, properties that we associate with this. This wave has a speed, a frequency, a wavelength, and time for some new ones now, and things we'll call an angular frequency. We call it omega, and a wave number, K. So we're introducing these new guys, omega and K, the angular frequency and the wave number. So let's talk about these little bits. Angular frequency, right? Emphasis. There are 2 pi radians in one oscillation. If I go once around, what have I done? Right? I've done different versions. 360 degrees. One oscillation. 2 pi radians. They're all the same thing. They're different ways to represent the same concept of going once around. So 2 pi radians is equal to 1 oscillation. Right? So I can relate the angular frequency to the regular frequency by just basically a unit conversion. 2 pi radians in 1 oscillation times F. Omega is 2 pi F. Could also express it in terms of the period. Right? So, period. I'll leave that with a capital T. Right? And period is the time to complete one oscillation. Right. Well, the frequency is how much time transpires in 1 second, and period is how much time to do one oscillation. They're inverses of each other. The frequency is 1 over the period, which correspondingly means that the angular frequency is 2 pi over the period. If you remember your circular units, this should remind you when you did circular rotations. Right. Similarly, we have this K. K is the wave number and is equal to 2 pi over the wavelength. 2 pi over the wavelength. All right. So yes, we've introduced a dozen more equations. It's like 3 new equations, and you've seen this before, guys. Right? But why? Why did we bother, okay? Why did we bother introducing these? That is a fair question. And I'll give you the sentence answer, and then we'll work it out to explain why. And the simplest way for me to say it is that K and omega, they mathematically describe waves. They mathematically describe the waves. Come on. in natural units. And I do mean like air quotes here, natural units. But they are the natural way to describe waves, these k's and omegas. So let's put this in some context, okay? First, we're going to start writing functions to represent these. And we're going to do bad case first. Bad case. I'm going to have what I call f0 as a function of x. And it's going to be straight sine of x. X, f0. Come on. So what's the wavelength of this thing? Well, the wavelength is, come on, 2 pi. But I'll say this is just a bad form, terrible form. When we're thinking physically, when we're doing physics problems, x normally has units of length. All right? But sine hates operating on things with units. In fact, sine must have dimensionless quantities. All right? And it just comes back from the definition of our trig functions, all right? Like, here's some angle theta, x, y, r. Sine of theta is equal to the ratio of x over r in this picture. And that's dimensionless. So let's try again. Let's do a little bit better. Let's make the argument dimensionless. So we'll have what I'll call f1x. And this is going to be sine of x over a, where a is something that has units of length. Well, what does my plot look like now? f1. It'll be a longer wave. It'll be longer. What's the wavelength of this thing? There, the wavelength is 2 pi times a, this quantity we've introduced. All right. So why introduce a? Just skip it. Let's just express this in terms of its wavelength. So now we'll get to what I call the best form. If I ever get my black ink back. Come here. So we'll have f2x. Instead of this a quantity, let's express this correctly. We'll say this is sine of 2 pi over the wavelength x. X, f2. What does this look like? Well, it's going to be a sinusoidal wave again, but progress. What's this distance? It's just the wavelength. The wavelength is just equal to itself now. None of these weird scaling things in the universe. So, and you might notice that. So this f2x So this f2x is just equal to sine of kx. And that's what I mean by expressing this in its natural units. It's natural units. So let's put in the full picture now. Full picture, right? Waves will have both coordinate dependence and a time dependence. So waves are functions of both of coordinates x, y, z and time. That's important. And let's finally express our electric and magnetic fields as wave functions. We'll have E of Tx. It's going to equal some maximum amplitude times sine of omega t minus plus, could be either, kx. The magnetic field is a very similar expression. It is 1 over the speed of light times the previous expression, with the caveat that Emax equals C Bmax. Must be true. All right. So some notes on this. The minus plus. Well, what's that about? Okay. If I have a function that is minus kx, that's a wave traveling to the right. That's a wave traveling in the positive x direction. If I have plus kx in my expression, well, that is a wave traveling in the other direction. Traveling in the negative x direction. You want to convince yourselves of these? Do the simplest plot you know. Y equals x. So we're going to do this. Right. So the first time we're going to say y equals x. And what does that plot look like? Well, it goes through the origin. Now let's do y equals x minus 1. We subtract some number off. Minusing shifts the curve to the right. Now the curve has shifted like that. Try again. We'll shift it one more time and go x minus 2. And now we have a curve that's further and further to the right. So by subtracting, we're taking our function, our plot, and just shifting to the right every time. Emphasis. Subtracting shifts to the right. All right. We'll do one more practice problem, then we'll call it in here. All right. So, practice problem. Let's actually do something with this new knowledge. And I'm going to give you the electric field. E of Tx is equal to this. It's minus 375 volts per meter times the sine of, I'm going to use square brackets, sine of 5.97 10 to the 15th radians per second times time plus 1.99 10 to the 7th radians per meter times x. There's our electric field wave equation. So, A is a field traveling left or right. All right. For that answer, we need the plus sign on the x term. So the plus sign on the x term tells us that this is a wave going to the left. Come on. Next, what is Emax and Bmax? Well, for that, we just read straight off of the equation. We say, look, there's Emax, the maximum amplitude. So Emax, don't worry about the signs, all right? When we're talking about maximum, all you care about is the magnitude. The minus sign there is just to throw you off. Another way to think of it, you can do it as a phase change of the sine functions. We can talk more about that later. What do I mean by phase shifts? Basically, take your sine curve and shift where it's at. That's a phase change. And that can be expressed as this -1 out front. So altogether, Emax is just going to be the 375 volts per meter. Whereas Bmax, don't forget the relationship through the speed of light, is going to be 375 volts per meter divided by the speed of light, which I'll let you calculate this out to verify. It should be 1.25 micro Tesla. All right, next part. What is the frequency and wavelength? So, call back. Omega is 2 pi f. So f is omega Omega you can read straight off of the equation. The omega is the term multiplying time. So there is that 5.97 times 10 to the 15th radians per second, all divided by 2 pi. We'll find that the frequency itself is going to be a 9.5 times 10 to the 14th hertz. You can get the wave number by reading it off the equation. And we can relate the wave number to the wavelength that we want to find. The wavelength is 2 pi over that wave number. So there we have 1.99 times 10 to the 7th radians per meter, all underneath the 2 pi. And if you calculate that, you're going to find this is 3.16 times 10 to the -7th meters, or 316 nanometers. Last part. Is this wave in the visible spectrum? Well, let's give you a range, okay? The visible spectrum, Roy G. Biv, your rainbows, right? The visible spectrum is about, this will change person to person depending on your biological makeup of your eyes, but for most people, this is generally accepted. we can see as tiny as 380 nanometers. Right? The lowest wavelength we can see, and the longest wavelength we can see is 740 nanometers. All right? So, short wavelength, high frequency, right? This is close to a blue. This is closer to a red. Our wave, right? Our wavelength is less than blue, which frequency terms means is out of the spectrum it's about an ultraviolet ray, or UV for short. All right, so with that, we'll call it into this video, and I'll see you all next time.